Hi everyone. On this troubleshooting guide, we'll go through a structured way to troubleshoot bus error alarms and random HMI or CNC screen freezes on Mori Seiki SL80 machines using a Fanuc 15TA control. This is designed for maintenance and automation teams, and it follows a real failure pattern that ultimately led to a confirmed CNC rack backplane failure. The goal here is to help you catch the problem early, avoid unnecessary board swaps, and document what you find in a clean, repeatable way. 1. What problems are we covering? Here's what we're looking at. You might see intermittent or persistent bus error alarms, random freezes where the HMI stops responding or the CNC screen stops updating. Sometimes you'll also notice a loss of communication between CNC boards. And in the worst cases, the issue escalates over time until the backplane has a hard failure. Before you start any hands-on work, make sure you've captured at least one photo of the screen and the rack layout. 2. Safety first. Always. Safety isn't just a guideline. It's the priority every time you work on the Fanuc 15TA CNC or Mori Seiki SL80. Before you approach the electrical cabinet, remember, always follow your site's lockout-tagout procedures. This step protects you and those around you from unexpected hazards. When handling circuit boards, use ESD protection. Electrostatic discharge can damage sensitive components, even if you don't see it happen. Don't risk turning a simple fix into an expensive repair. Never hot plug boards unless the OEM specifically allows it. On these older controls, plugging or unplugging boards with power on can escalate a minor issue into a major failure. These rules aren't just about compliance. They're about protecting equipment, and most importantly, protecting you. Stay vigilant. Your safety comes first, always. 3. Quick architecture recap. Why backplane matters. Let's do a quick architecture summary. You've got a CNC rack with a backplane, also called a bus board. That backplane distributes both power and bus signals across the rack. The key boards we see most often on Fanuc 15TA systems include Base 0, O1P1E, the main CNC base/master CPU board. If this one fails, the CNC can't operate. PMC, O1P27, runs ladder logic, PLC logic, and talks to machine I/O. And Base 2, O1P24, is the third-level CNC base expansion board, used for extended CNC capability beyond Base 0 in this configuration. So here's the key takeaway. If the backplane is degrading, it can cause weird intermittent behavior. BLS errors, freezes, communication glitches, before it finally fails completely. 4. The failure pattern we typically see. In the failure pattern we observed, the story usually goes like this. First, you get a freeze once in a while, and a reboot clears it. Then the bus error alarms start showing up more often. Eventually, the machine freezes even while idle. No motion, nothing running. And the alarms become non-deterministic, meaning they're not tied to one axis or one operation. At the end of that path, the backplane is confirmed as failed. Troubleshooting workflow. Follow in order. Step 1. Symptom Verification. Step 1. Confirm and document the symptom. Record the exact alarm text, alarm code, and timestamps. This is important because intermittent bus issues can change across restarts. Also check the hardware LEDs on the boards. The Fanuc maintenance manual notes that if the display function isn't working, the LEDs on the PCBs may be the only indicator of faults, so don't skip that LED check. Now capture operating state. Was the machine idle? Jogging? In auto? Spindle on or off? And check the scope of the freeze. Is it HMI only, meaning CNC still runs but the screen is stuck? Or is it a hard freeze, where both CNC and HMI stop updating? Finally, reboot and observe. Does it recover temporarily? If yes, that's a clue that something is degrading, rather than an immediate hard short. Key indicators pointing to bus or backplane issues. random behavior not tied to a program, freezing even at idle, and different alarms across restarts. Step 2. Environmental and external factors. Step 2 is environmental and external checks. Verify cabinet temperature and confirm fans are working. Inspect for dust, oil mist, or condensation. Any contamination can cause instability. Check cabinet grounding and shielding. Noise issues are real on these controls. And ask, did something change recently? Retrofits, board replacements, rewiring? Anything that could have disturbed connectors or cable routing? Action here. Clean filters and fans, and fix grounding problems before moving forward. If you don't stabilize the environment, you can chase ghosts all day. Step 3. Power supply validation. Critical. Step 3. Power supply validation. This is critical. Measure logic rails at the CNC rack, not just at the power supply. Focus on +5 VDC first. This is the most sensitive rail. Also measure +1-2 VDC. And measure under load, not only when the machine is sitting idle. What you're looking for is ripple, dropouts, or instability, especially during the moment a freeze happens. Pass criteria. Voltage stays within OEM tolerance and does not fluctuate during freeze events. If power is not clean, test with a known good supply before you start condemning boards. Step 4. Visual inspection and reseating. Step 4. Power off, lockout, and reseat. Power off and apply LOTO. Remove and reseat the boards in the rack. Inspect the backplane connectors, look for bent pins, oxidation, burn marks, and confirm the card guides and retention hardware are solid. Important note: if reseating improves the problem temporarily, that's a strong sign you're dealing with connector or backplane degradation. Step 5. Isolation by elimination. Step 5. Isolate by elimination. If you have spares, test with a known good CPU board, and if possible, a known good HMI or MDI. Watch whether bus error persists. Key indicator: if bus error remains even after swapping CPU and HMI, the backplane moves up to the top of the suspect list. Step 6. Bus load and slot sensitivity. Step 6. Check slot sensitivity if your configuration allows it. Move non-critical boards to alternate slots, one at a time. Then observe whether the errors change in frequency or behavior. Strong evidence. If errors are tied to a specific slot position, that points to a localized backplane issue. Step 7. Confirm backplane failure. Step 7 is confirmation. Backplane failure is the most likely root cause if 2 or more of the following are true. You have random, irreproducible bus error alarms. Freezing happens even when the machine is idle. Reseating boards temporarily improves it. Power rails are verified OK. Boards test OK individually. And errors are slot-dependent or position-dependent. Case conclusion: the freezing and bus error resolution. Let's wrap up the case with the final conclusion. On the left, you see the initial state of the system. The control was in a critical fault condition, showing a bus error, with the system effectively unrecoverable at the CNC level. At this stage, the failure was unresolved, and all evidence pointed to instability on the CNC bus, specifically a developing backplane issue. On the right, you see the final state after corrective action. The system is fully operational, displaying actual position data, confirming that normal CNC execution has been restored. The backplane was replaced, validation was completed, and the control returned to a stable, production-ready state. The key takeaway is shown at the bottom. By following the full 7-step diagnostic funnel, unnecessary and costly component replacements were avoided. The power supply, base 0 and base 2 boards were methodically eliminated as root causes, allowing the backplane to be definitively identified. After replacing the backplane and resolving a secondary door interlock circuit issue, full spindle operation was restored. Final validation confirmed successful operation at 500 RPM using Gear 4, and the machine was safely returned to production. This case highlights why structured diagnostics matter. Random bus errors and screen freezes are often early warning signs of backplane failure, not isolated board defects. Thank you for watching. Remember, a disciplined diagnostic approach leads to reliable solutions. See you next time.